Chapter 3. Convolutional Neural Networks, CNNs. 3.1 Understanding Convolution Operations. Convolutional neural networks, CNNs, represent a significant leap in the performance of neural networks in tasks involving image recognition, video processing, and even non-visual tasks like natural language processing. The fundamental building block of CNNs is the convolution operation. Understanding this operation is crucial for grasping how CNNs learn and make sense of spatial data like images. In its essence, a convolution is a mathematical operation that involves two functions, producing a third function that expresses how the shape of one is modified by the other. When applied to the context of image processing, the first function is the image itself, often conceptualized as a two-dimensional array of pixel values. The second function is called a kernel or filter, which is a smaller two-dimensional array. The convolution operation performed in neural networks involves sliding the filter across the image, performing an element-wise multiplication followed by a sum. Each position of the filter as it slides over the image corresponds to a small region of the image called the receptive field. The values obtained from the element-wise multiplication are summed up to produce a single pixel in the output. This output is known as the feature map or convolved feature, and its role is to highlight specific features in the image, such as edges, texture, or shapes. By applying various filters, a convolutional layer can extract a variety of such features from an input image. The movement of the filter across the input image is governed by two parameters, stride and padding. The stride determines how many pixels the filter jumps over as it moves across the image. A stride of 1 means that the filter moves 1 pixel at a time, resulting in a densely sampled feature map. Increasing the stride reduces the spatial size of the feature map and increases computational efficiency, but may result in the loss of finer detail in the output. Padding involves the addition of extra pixels around the border of the input image. These pixels are usually set to 0 and are known as zero padding. Padding preserves the spatial size of the output feature map, allowing deeper networks to be built without size constraints, and helps the CNN to capture information around the edges of the image. Padding can be same, where the output size is the same as the input size, or valid, where no padding is applied and the output size is smaller. The convolution operation introduces two critical properties into CNNs: sparse interactions and parameter sharing. Sparse interactions mean that the output is computed using only a small number of inputs, vastly reducing the number of parameters compared to a fully connected layer. This local receptive field captures local dependencies and leads to a more efficient learning process. Parameter sharing involves using the same filter for each receptive field in the input, reducing the number of unique parameters the network has to learn. This feature exploits the fact that if a pattern or feature is useful to compute at one location, it is likely to be useful at another, providing invariance to translation. Once the feature map is generated, a nonlinear activation function is usually applied. This is often the rectified linear activation unit, ReLU, or one of its variants. The activation function introduces nonlinearity into the processing, allowing the network to learn and model complex patterns and interactions among the features. Without nonlinearity, the neural network would be constrained to modeling only linear relationships, severely limiting its expressive power. The next step in the operation of a convolutional layer is typically the pooling or subsampling layer, which reduces the spatial size of each feature map. Pooling layers combine the outputs of neuron clusters at one layer into a single neuron in the next layer. Max pooling, which involves taking the maximum value from a set of values, is one standard approach used to achieve this dimensional reduction. Pooling provides a form of translation invariance, and like striding, makes the detection of features robust to small changes and variations in the input image. It also contributes to reducing the computational load and the risk of overfitting by summarizing the presence of features. The concept of depth is also crucial in a convolutional neural network. Depth refers to the number of filters used in each convolutional layer. Each filter detects different features, and stacking these layers on top of one another allows the network to detect complex patterns. Early layers may detect simple edges, while deeper layers concatenate these features to understand more complicated structures such as textures or objects within the image. As we progress through the layers, the level of abstraction increases, and the model's ability to capture complex concepts improves. Training a convolutional neural network involves the use of backpropagation and optimization algorithms, similar to any other neural network. However, due to the convolution operation and the resultant architecture, this training process, while conceptually similar, exhibits unique properties and challenges. It requires careful consideration of the size and depth of the network, the choice of filters, and the methodologies for regularization and hyperparameter tuning. With the proper design, CNNs can be adept at handling the vast volume and high dimensionality of the data encountered in modern applications. A skilled understanding of convolution operations is paramount for an individual or team looking to employ convolutional neural networks effectively. It lies at the core of its powerful ability to manage, interpret, and learn from image data. By manipulating filters, stride, and padding parameters, a data scientist or developer can greatly influence the behavior and performance of a CNN. It is the mastery of this rudimentary operation that often dictates the success of CNNs in achieving impressive results on a myriad of tasks in computer vision and beyond. 3.2 Layers in CNNs: Convolution, Pooling, and Fully Connected. Convolutional neural networks, CNNs, are a specialized kind of neural network used for processing data with a grid-like topology. Examples include time series data, which can be thought of as a 1D grid taking samples at regular time intervals, and image data, which can be thought of as a 2D grid of pixels. The exceptional ability of CNNs to handle pixel data makes them highly suitable for image recognition tasks, such as identifying faces, objects, and traffic signs, among many other applications. In this chapter, we will delve deeply into the layers that make up CNNs: convolutional layers, pooling layers, and fully connected layers. The first layer type in a CNN is the convolutional layer, which is the core building block of CNNs. The primary purpose of this layer is feature detection. Unlike fully connected networks that connect every input to every output, convolutional layers connect local regions of the input to the output. These layers consist of a set of learnable filters or kernels which are small spatially, along width and height, but extend through the full depth of the input volume. For each filter, the convolution operation involves the filter moving across the input image, which can be imagined as sliding a small window over the larger image. At each location, a matrix multiplication is performed and sums up the results into a single value in the output feature map. The result is a transformation that converts spatial input patterns to abstracted form in the output. An important concept in the context of the convolutional layers is the idea of stride and padding. Stride refers to the number of pixels by which we slide our filter across the input. A stride of 1 means we move the filters 1 pixel at a time, while a higher stride value means we move the filters with larger steps. On the other hand, padding refers to adding extra pixels around the border of the input image. This allows for more flexibility in how the filter interacts with the borders and helps maintain the spatial size of the output volume. If padding is not used, the spatial size of the output feature map will be smaller than the input due to the convolution operation. After the convolutional layer, the next common layer in CNNs is the pooling or subsampling layer, which reduces the dimensionality of each feature map but retains the most important information. Pooling layers simplify the outputs by performing a downsampling operation along the spatial dimensions, width, height. This reduction in resolution serves to decrease the computational load and improves the robustness of the network. The most common approach to pooling is max pooling, which takes the largest element from the rectified feature map within a certain size window. However, there are also other pooling techniques, such as average pooling and L2 norm pooling. The pooling layers serve multiple purposes. They progressively reduce the spatial size of the representation, which lowers the number of parameters and computations in the network, thus curtailing overfitting. They also enable the network to achieve spatial variance, making the representation invariant to small translations in the input. For instance, in a max pooling layer, no matter where in the pooling window a prominent feature appears, it will be captured by the pool neuron. This translational invariance is particularly useful when we want to detect features regardless of their spatial position in the visual field. Once several convolutional and pooling layers have been stacked, the high-level reasoning in the neural network is done via fully connected layers. A fully connected layer takes all neurons in the previous layer, whether they are part of convolutional or pooling layers, and connects them to every single neuron it has. Typically seen as the final layers of a CNN, these layers integrate the localized information learned by earlier convolutional and pooling layers to perform classification. The neurons in a fully connected layer have full connections to all activations in the previous layer, as seen in regular neural networks. Their activations can hence be computed with a matrix multiplication, followed by a bias offset. The architecture of fully connected layers brings forth a necessary point about the flatten operation. Before forwarding the output of a pooling layer to a fully connected layer, the 2D matrix should be flattened into a vector, which involves reshaping the 2D output into a 1D array. This is needed because fully connected layers expect input to be a single vector of values, rather than a 2D matrix. This conversion from spatial representation to a flat, dense vector allows for the final decision-making process in the neural network to occur. To prevent overfitting, especially when fully connected layers have a high number of parameters, regularization techniques such as dropout can be quite effective. Dropout consists of randomly disabling neurons in a network during training to prevent the network from becoming overly reliant on any particular neuron. When implemented correctly, dropout can significantly improve the performance of neural networks on unseen data, as it forces the network to learn more robust features that are not dependent on the presence of certain other features. Another crucially important component in CNNs is the activation function, which is applied to the output of every convolutional and fully connected layer. Without activation functions, the network would consist only of two linear operations, convolution and matrix multiplication, which are themselves linear. This would limit the network to only being able to represent linear mappings from inputs to outputs. Activation functions introduce nonlinearity into the model, enabling it to learn more complex relationships within the data. The most commonly used activation function in CNNs is the rectified linear unit, ReLU, because it introduces nonlinearity while mitigating the vanishing gradient problem that is present with functions like the sigmoid or tanh. The combination of convolutional layers, pooling layers, and fully connected layers in a CNN results in a powerful hierarchical model. The initial layers, typically convolutional layers, are responsible for learning local features such as edges and textures. The middle layers learn to combine these local features to form larger features like motifs and patterns. The final layers, usually fully connected, then use these larger features to make predictions, such as classifying an image. This hierarchical learning strategy is a key reason why CNNs perform so well on tasks involving visual data. Training a CNN involves learning weights in the convolutional layers and fully connected layers. This process is completed using backpropagation, which is a standard gradient descent algorithm adapted for function compositions, relying on the chain rule to compute gradients. Each weight is updated to minimize the loss function, which is a measure of the difference between the actual output of the network and the expected output. Additionally, techniques such as learning rate decay, momentum, and adaptive learning rate algorithms like ADAM can be applied to improve the convergence of the learning algorithm. Finally, it's important to note the role of architectural decisions in the construction of CNNs. Selecting the number of layers, their types, convolutional, pooling, or fully connected, the size of filters, the number of filters, the use of padding and stride, and the placement of dropout and normalization layers are all critical choices that affect the performance of the network. It is often through significant experimentation and testing, and sometimes guided by principles and practices that have proven effective in the past, that effective CNN architectures are developed. These networks are then painstakingly trained using large datasets and evaluated against validation sets to ensure they generalize well and do not overfit the training data. Only through this iterative process of design, training, and validation can optimal CNN architectures be developed for specific tasks. 3.3 Architectures: LeNet, AlexNet, and VGG. Convolutional neural networks, CNNs, represent a milestone in the evolution of neural network architectures, specifically tailored to handle the complexities found in high-dimensional data, such as images and videos. The foundational architecture that established the use of CNNs in practical applications is LeNet 5, developed by Yann LeCun in the late 1990s. This network was initially applied to the problem of digit recognition and demonstrated the potential of CNNs for computer vision tasks. LeNet 5 consists of a series of convolutional layers followed by subsampling layers, also known as average pooling layers, and fully connected layers. The convolutional layers operate as feature detectors, extracting hierarchical features from the input images, while the subsampling layers reduce the spatial resolution of the feature maps, increasing the receptive field and reducing the number of parameters. LeNet 5's architecture is uncomplicated by modern standards, consisting of two convolutional layers with 10H activations, interleaved with average pooling layers, and ending in 3 fully connected layers. The input to the network is a 32 by 32 pixel image, which is then passed through the convolutional layers. The use of convolutional layers enables the network to be invariant to small translations in the input image, an essential characteristic for recognizing the same object in slightly different positions. LeNet 5 was trained using backpropagation and the gradient descent optimization algorithm, and was one of the first models to demonstrate the practical capabilities of CNNs in processing visual information. Following the foundational work of LeNet 5, the field of deep learning witnessed a renaissance, led by the introduction of AlexNet in 2012. AlexNet was instrumental in rekindling interest in CNNs, primarily because it significantly outperformed existing methods in the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC. AlexNet is deeper and wider than LeNet 5, consisting of 5 convolutional layers, some of which are followed by max pooling layers and 3 fully connected layers. It introduced several key innovations to CNN architecture: the use of rectified linear units, ReLUs, as activation functions, which helped in alleviating the vanishing gradient problem, normalization layers, later shown to be of minimal impact, and the use of dropout as a regularization method to reduce overfitting. The AlexNet architecture begins its processing with an input image size of 227 by 227 pixels. The size of the receptive fields in the convolutional layers and the stride with which they are applied also differ, allowing the network to learn a more complex hierarchy of features. Additionally, an important practical consideration in training AlexNet was the use of parallelism. Due to the limitations in computational resources at the time, the original AlexNet was trained on 2 GPUs, with the model's layers split between them. This parallel training approach leveraged the capabilities of GPUs to dramatically reduce training times and allowed for larger and deeper networks to be efficiently trained. Building on the success of AlexNet, the VGG network was proposed by the Visual Graphics Group, VGG, at the University of Oxford and presented in 2014. While AlexNet can be seen as an expansion and refinement of the principles found in LeNet 5, VGG represents the next step in CNN architecture by standardizing the convolutional layer design. VGG contains very homogeneous and deep architectures with up to 19 layers. During its development, multiple versions of VGG were tested, commonly referred to as VGG 16 and VGG 19 based on their number of layers. VGG's key contribution was to show that the depth of the network is a critical component for achieving higher levels of performance. The architecture of VGG is characterized by its use of a very large number of filters that have smaller receptive fields, 3 by 3, with a stride of 1, compared to the larger filters used in previous architectures. These smaller filters are used consistently throughout the network, which helps in capturing finer details in the image. They also contribute to capturing more complex features as the depth increases. Pooling layers divide the spatial resolution by 2 after each series of convolutional layers, progressively reducing the dimensions of the feature maps while deepening the network. In VGG, the architectural uniformity simplifies the hyperparameters management even as the network's depth increases. VGG also introduced the use of 1-by-1 convolutional filters, which can be interpreted as a linear transformation of the input channel's depth that is applied at every spatial position of the feature maps. This allows for more complex combinations of features at different depths within the network, and it added to the network's representational capacity without increasing the spatial dimensions of the feature maps. Through these advancements, VGG improved upon the results set by AlexNet on the ILS-VRC, and further showed that networks with more weight layers could lead to better performance. The trade-off, however, is the significantly larger number of parameters and computational resources required to train and deploy VGG networks. Despite this, the feature representations learned by VGG have proved to be highly transferable and beneficial for various tasks beyond image classification, including object detection and image segmentation. Both AlexNet and VGG utilize data augmentation techniques to address overfitting, a method which has since become a standard practice. Data augmentation includes making modifications to the training images, such as random crops, rotations, and color alterations, thus artificially increasing the diversity of the training dataset. This approach helps the networks to generalize better to new, unseen images by simulating various transformations that might occur in real-world scenarios. It also mitigates the risk of the models learning too closely from the limited training data, effectively improving their performance on external datasets through enhanced robustness. While LeNet laid the groundwork for the use of convolutional layers, AlexNet and VGG evolved the architecture into deeper and more complex networks that could leverage the rapidly increasing computational power of GPUs. These developments began a trend towards deeper neural networks, where the complexity of the model is proportionate to its ability to learn from vast amounts of data. It became apparent that models with increased depth and capacity, when trained on large, rich datasets, could surpass more traditional approaches and even achieve near or superhuman accuracy on certain tasks. This realization sparked a wealth of research on how to effectively increase the depth and capacity of neural networks without running into issues such as overfitting or unmanageable computational requirements. In summary, the advancements made by LeNet, AlexNet, and VGG have had a profound impact on the field of computer vision and on the design of neural networks. Each architecture introduced significant changes and improvements that have informed the development of subsequent generations of CNNs. These include innovations in network depth, use of non-saturating activation functions, strategies to prevent overfitting, and more efficient use of computational resources, such as GPU acceleration. The impact of these architectures is still evident in the most advanced CNNs today, which build upon the principles laid down by these pioneering models to tackle more complex and diverse tasks across a multitude of domains. 3.4 Advanced Architectures, ResNet and Inception Networks. As we delve into the domain of advanced neural network architectures, it is critical to start by appreciating the contributions of traditional convolutional neural networks, CNNs. These CNNs are paramount in various computer vision tasks, establishing themselves as the backbone of image recognition, object detection, and more. However, standard CNNs begin to falter as they grow deeper, a phenomenon known as the vanishing gradient problem, where the gradient, the signal used to update weights, becomes increasingly smaller until it no longer contributes effectively to the learning process. To address such challenges, the deep learning community has proposed various sophisticated architectures, with residual networks, ResNet, and inception networks being two prominent examples. These models introduce unique elements that strengthen the power and efficiency of neural networks, particularly for tasks requiring the processing of visual information. The ResNet architecture addresses the degradation problem by introducing the concept of skip connections, also referred to as residual connections. The central idea is to add the input of a layer onto the output of a layer deeper in the network. These connections encourage the flow of gradients through the network, making it possible to train significantly deeper networks than what was previously feasible. With a properly trained ResNet, it is plausible to have networks that are hundreds of layers deep, learning successfully. In these networks, layers do not necessarily learn the desired mapping, but the difference or residual between the input and the desired output. This insight is simple yet profound, as it mitigates the risk of vanishing gradients by allowing an alternate shortcut path for the gradient to flow through the network during backpropagation. Inception networks, on the other hand, are another pivotal architecture that focus on how we can efficiently scale up CNNs while maintaining computational practicability. Inception networks implement a module-based design where each module comprises a series of convolutions at different scales, allowing the network to capture information at various granularities. By including various convolutions with different kernel sizes in parallel, as well as pooling operations within the same module, the inception networks can process information at multiple scales and then aggregate this information efficiently. The advantage of this is twofold. It increases the model's expressive power, and it also controls the computational cost despite an increase in depth and breadth. The original inception network, GoogleNet, was able to achieve substantial improvement in performance on image recognition tasks. This was largely due to the network's ability to look at an image in various scales and contexts simultaneously, hence obtaining a richer set of features compared to what a traditional CNN would gather. As the iterations of inception networks advanced, they saw elaborations on this concept with further factorization of convolutions to reduce computational resources, and with more sophisticated ways of parallelizing various kernels. Inception v4 and the Inception ResNet hybrids are such examples where the robustness of ResNet was combined with the Inception architecture, leading to even further improvements in performance. Discussing the benefits of ResNet further, we see that the architecture's true breakthrough is its simplicity in solving deep learning problems. The residual blocks, which contain the skip connections, are designed in such a way that adding additional blocks, essentially stacking more layers, does not hinder the network's performance and in many cases enhances it. This scalability means that researchers and practitioners have the flexibility to adjust the depth of a ResNet according to the complexity of the task at hand, without running into issues such as the vanishing gradient problem. Another significant advancement in ResNet architectures came with the introduction of bottleneck blocks. These blocks utilize one-by-one convolutions, known as pointwise convolutions, to reduce the dimensionality of input feature maps, hence decreasing the computational load before applying the more costly 3x3 convolutions. Afterward, another one-by-one convolution is used to restore dimensionality. This design choice reduces the number of parameters and the computational expense without sacrificing the capacity to learn complex features, paving the way for even deeper networks. The Inception network's forward-looking approach has also paved the way for modern CNN architectures. By juxtaposing smaller convolutions alongside larger ones, the network caters to capturing patterns that might be spatially larger or smaller in scale. This multi-scale processing is done within the network itself, without requiring a pre-processing step to resize or crop the images into different scales, thus saving on pre-processing time and resources. Moreover, normalization techniques introduced within Inception modules have been integral in stabilizing the learning process and allowing for faster convergence. Furthermore, the introduction of auxiliary classifiers in the Inception architecture serves a dual purpose. They help in combating the vanishing gradient problem by introducing additional gradient signals into lower layers, and they provide regularization that aids in preventing overfitting. Although these classifiers are only used during the training phase, they embody a clever design that promotes healthier gradient propagation throughout the depths of the network. When considering the adaptability of these advanced architectures to different tasks, both ResNet and Inception networks stand out for their versatility. ResNet's approach to residual learning can be applied not just in visual tasks, but also in audio, time series data, and generative models, showcasing its broad applicability. Likewise, the Inception architecture has inspired a myriad of task-specific adaptations, illustrating the flexible nature of its module-based design. This adaptability has been crucial in pushing forward the limits of what can be achieved with deep learning in various domains. Lastly, the impact of these architectures on the efficiency of training deep neural networks cannot be overstated. ResNet, with its ability to ease the training of substantially deep networks, and Inception networks, with their capacity to manage computational resources through effective and novel structuring of layers, have changed the landscape of neural network design. Both architectures have influenced countless subsequent models and remain central references for those exploring new horizons in neural network designs. With the incorporation of these architectures, deep learning systems have reached unprecedented levels of accuracy in tasks across the spectrum of artificial intelligence. As the field of deep learning progresses, the principles introduced by ResNet and Inception networks will undoubtedly continue to inform and inspire the development of new, more sophisticated architectures. The persistence of the core ideas behind these models, residual learning, feature aggregation at multiple scales, efficiency through design, is testament to their significance in the advancement of convolutional neural networks. The study of these architectures is essential for any practitioner looking to understand the state-of-the-art in neural network research and to build upon the rich foundation they provide. 3.5 Techniques for Visualizing and Understanding CNNs. Visualizing and understanding the inner workings of convolutional neural networks, CNNs, is crucial to improving neural network architecture design, debugging models, and fostering transparency for broader acceptance. This section provides an extensive examination of established methods for interpreting what CNNs learn, how they make decisions, and where they might fail. One seminal technique for visualizing CNNs is the generation of activation maps, which involve producing heat maps corresponding to the areas of the input image that activate certain filters in the network layers. These maps are particularly revealing at the early layers, where visualizations may show that CNNs learn to detect edges, corners, and textures. As visualizations progress deeper into the network, they typically correspond to higher-level features, making direct interpretation more challenging. Nevertheless, observing activation patterns aids in confirming whether the network learns hierarchies of features indicative of sophisticated learning. Another pivotal visualization tool is the deconvolution of activations, which aims to project feature activations back to the input space. This technique, often referred to as deconvnet, allows researchers to see which input patterns contribute to high-level feature activations. By reversing the flow through the network and utilizing transpose operations corresponding to the convolutional layers, deconvnet helps in decoding the learned representations and understanding the hierarchical structure of CNNs, thus providing insights into the pattern analysis done by the neural network. GradCam, or Gradient-Weighted Class Activation Mapping, enhances the interpretability of CNNs used for tasks such as image classification by highlighting important regions in the image for predicting the class. It uses the gradients of the target concept flowing into the final convolutional layer to produce a coarse localization map, emphasizing important regions for the prediction of that concept. This technique is beneficial because it can be applied to a wide range of CNN models without requiring architectural changes or retraining. Layer-wise relevance propagation, LRP, is yet another approach for interpreting CNN decisions. LRP redistributes the predicted output back through the layers of the network, attributing relevance scores to individual pixels in the original input image. This backwards redistribution is based on a set of rules derived mathematically to preserve the output across layers, thereby providing pixel-wise scores that indicate the importance of each pixel for the given prediction. It addresses the need to understand which parts of the input contribute to a net's decision and to what extent. Complementary to LRP is the concept of guided backpropagation, which modifies traditional backpropagation by only allowing positive gradients to flow back to the input. This process results in visualizations that emphasize the input features that have a strong positive influence on the target class and filters out those that do not. Guided backpropagation thus affords clearer, more focused illustrations of feature importance relative to other methods that take into account both positive and negative contributions equally. Feature visualization through optimization is an approach that involves tweaking an input image so that it maximizes the activation of certain neurons. By optimizing an input to excite individual filters, one can probe the learned features at different layers. The resulting images often showcase abstract representations of the feature detectors formed by the CNN. These visualizations can be mesmerizing and intricate, and they reveal the complexity of the patterns that the network is capable of recognizing. Network dissection is a quantitative approach for interpreting CNN behavior. By labeling individual units in each hidden layer with semantic concepts, researchers can evaluate how well different units correspond to understandable visual concepts. This method systematically studies the representations and quantifies the interpretability of individual units by comparing their activations to a set of predefined semantic categories. This approach not only affords insights into what each unit detects, but also provides a way to compare interpretability across different models. Dimensionality reduction techniques like TSNE, T-distributed stochastic neighbor embedding, are used to visualize high-dimensional data, including CNN activations, in 2 or 3 dimensions. By projecting activations of the network layers into a lower dimensional space, we can examine how different inputs, classes, or features cluster together. This offers a macroscopic view of the network's internal representations and can reveal patterns that inform understanding of learned abstractions or even biases inherent to the model. Finally, adversarial examples are quite informative in understanding CNNs, although they are often used to challenge them. By making deliberate, often imperceptible changes to an input image, one can confuse a network to misclassify the input. Studying these adversarial inputs and the corresponding CNN responses can offer valuable information about model robustness and the superficiality or depth of learning. The significance of the adversarial approach lies in its ability to test and critique the decision boundaries and feature sensitivities of CNNs. In summary, these techniques and several others form a suite of tools critical for visualizing, understanding, and refining CNNs. Each method provides unique insights. Some focus on individual layers, neurons, or filters, while others examine the collective behavior or the global decision-making process. The application of these methods ensures a more transparent view into the often opaque world of CNNs, allowing for responsible development and deployment of these powerful neural network models. By leveraging these tools, one can begin to unravel the complexities of convolutional neural networks, ensuring that they are not only effective, but also interpretable and trustworthy. 3.6 Applications of CNNs in Image Recognition. The application of convolutional neural networks, CNNs, in the field of image recognition has revolutionized how machines interpret visual data. Image recognition involves the identification and classification of objects within images, which is a complex task due to the variation in object appearance, lighting, and background. CNNs are particularly suited for this application due to their ability to automatically and adaptively learn spatial hierarchies of features from image data. This capability stems from the convolutional layers filtering process, where local receptive fields focus on small regions of the input data, allowing the network to build a robust understanding of visual patterns. The architecture of CNNs is inspired by the visual cortex in the human brain, where individual neurons respond to stimuli in a restricted region known as the receptive field. In the context of image recognition, the convolutional layers act as feature detectors, each extracting different aspects of the visual input. As an image passes through successive convolutional layers, the network learns increasingly complex patterns. Lower layers might detect simple edges or textures, while higher layers might recognize more complex structures, such as parts of objects or entire objects themselves. By stacking layers, CNNs can abstract and decompose visual information into manageable and interpretable components. One of the leading applications for CNNs in image recognition is within the realm of facial recognition. Through learning from vast datasets of facial images, CNNs can distinguish facial features and structures with remarkable accuracy, enabling applications ranging from biometric access control to social media tagging. These networks can handle variations in expression, pose, and lighting, which were significant challenges for earlier image recognition techniques. The ability to generalize from training data to new images allows CNNs to reliably identify individuals in different situations and contexts. Another critical area is medical image analysis, where CNNs assist in diagnosing diseases by recognizing patterns in imaging data that are often imperceptible to human eyes. They've been deployed to detect anomalies in various types of medical imagery, such as MRI scans, CT scans, and X-rays, potentially identifying conditions ranging from cancerous tumors to signs of neurological diseases. Their application helps radiologists reduce false negatives and positives, providing a powerful tool to complement medical expertise. In autonomous vehicles, CNNs play a vital role in recognizing and interpreting the car's surroundings to facilitate safe navigation. They process visual input from cameras mounted on the vehicle to identify and classify objects such as road signs, pedestrians, other vehicles, and lane markings. This information is crucial for decision-making processes in the vehicle's control system, enabling a response to dynamic road conditions. The accurate real-time processing of image data through CNNs is a cornerstone of the technologies underpinning the development of self-driving cars. CNNs also contribute to the advancement of robotics, where visual recognition capabilities are essential for interaction with the environment. Robots equipped with CNNs can differentiate between objects, determine appropriate grasping points, and navigate dynamically alongside humans in collaborative settings. This functionality is particularly beneficial for applications in manufacturing, logistics, and service robots, where visual recognition allows for greater autonomy and efficiency in completing tasks. In the consumer technology sphere, CNNs enhance the user experience through augmented reality (AR) apps that require fast and precise image recognition. For example, in mobile apps that overlay information onto real-world scenes, CNNs help identify objects and surfaces in the camera feed to position virtual elements accurately. Such capabilities enable engaging user interactions and create immersive experiences for gaming, shopping, and educational applications. Security and surveillance represent another domain where CNNs are used in image recognition. They can process and analyze video footage in real time to detect anomalies, unauthorized access, and other security incidents. By filtering through vast amounts of visual data, CNNs reduce the workload on human operators and increase the speed at which potential threats are identified. Their application in this area is a testament to their robustness and efficiency in dealing with complex and dynamic image sequences. Agriculture is yet another sector witnessing the impact of CNNs in image recognition. Farmers use CNN-powered systems to monitor crop health, detect pest infestation, and predict yields by analyzing drone and satellite imagery. These systems can process visual cues related to plant color, size, and morphology, providing insights that facilitate informed decisions on water, fertilizer usage, and harvest timing. The automation and precision offered by CNNs in this application considerably enhance agricultural productivity and resource management. Retail industry has seen a transformative impact with the integration of CNNs in image recognition for a range of applications. From inventory management systems that detect and track products to smart checkout solutions that automate the billing process, CNNs are streamlining operations and enhancing customer engagement. Additionally, Visual search tools powered by CNNs allow customers to find products by taking photos, seamlessly bridging online and offline retail experiences. In all these applications, the consistent factor is the ability of CNNs to learn from large, diverse datasets and improve over time. Through exposure to new images, these networks refine their parameters, enhancing their predictive accuracy. This property, known as generalization, is crucial for the sustainable deployment of CNNs in the dynamically evolving world of image recognition. The pervasive nature of image data and the universal need to interpret it make the proficiency of CNNs in image recognition a significant technological milestone in the pursuit of artificial intelligence. 3.7 CNNs for video analysis and object tracking. Convolutional neural networks, CNNs, have revolutionized the domain of video analysis and object tracking. These tasks are vital for numerous applications including surveillance, autonomous vehicles, and sports analytics, to name just a few. A CNN's ability to automatically and adaptively learn spatial hierarchies of features makes it uniquely suited for video data, which is fundamentally a series of images or frames. In video analysis, the frames are processed to detect and recognize patterns and anomalies, while object tracking involves identifying and following the trajectory of one or more objects across multiple frames. Both these tasks demand not only an understanding of individual frames, but also the temporal relationships between them. The approach to video analysis using CNNs starts with feature extraction. Similar to image analysis, convolutional layers detect features such as edges and shapes in the video frames. However, video analysis adds the complexity of temporal features, which are not present in static images. Temporal features represent the changes that occur across frames. To capture these, techniques such as 3D convolutions are used, which extend the convolution operation along the time axis, allowing the CNN to learn features from both space and time dimensions. This 3D convolutional approach is powerful because it maintains the spatial temporal information, which is paramount for understanding the dynamics within the video. Another prominent technique in video analysis is the use of two-stream CNNs, which involves running two parallel convolutional networks. One network processes the spatial information, individual frames, while the other handles temporal information, optical flow or frame differences. Optical flow maps movement between two frames and is particularly useful in capturing motion clues. By blending both spatial and temporal streams, the model gains a comprehensive understanding that aids in more accurate predictions and analysis of videos. This dual-stream approach is beneficial in scenarios such as action recognition, where the context provided by one stream might not be sufficient to recognize complex activities. In object tracking, CNNs are tasked with following objects as they move across different frames of a video. The challenge here is not only to detect the object in the initial frame, but also to recognize it in subsequent frames, even when its appearance might change due to various factors such as occlusion, illumination, or movement. CNNs handle this through a procedure known as fine-tuning, where a pre-trained network is slightly adjusted based on the initial frame information. This fine-tuning equips the network with a better understanding of the specific object of interest, allowing it to maintain track even when the object undergoes significant changes throughout the video. Siamese networks represent another innovative approach to object tracking using CNNs. Siamese networks use a unique architecture that inputs two different images and determines the similarity between them. For object tracking, one of the inputs is a reference image or patch of the object, while the other input is the current frame of the video. The CNN then assesses if the object in the current frame is the same as the reference. This way, Siamese networks are able to track objects over successive frames despite challenges such as scale changes or rotations. Recurrent neural networks, RNNs, are often used alongside CNNs for video analysis and object tracking, leading to models referred to as convolutional recurrent neural networks, CRNNs. RNNs are adept at handling sequential data, and when combined with the feature detection capabilities of CNNs, they become well equipped for video analysis. The RNN component can take the sequence of features extracted from the frames by the CNN and model the temporal dependencies between them. This combination allows for sophisticated modeling of video data that can learn both the spatial attributes of the frames and the temporal connections between them, significantly improving the video analysis. The real-world application of video analysis and object tracking with CNNs represents an intricate task, demanding the careful balance between accuracy and computational efficiency. While deeper and more complex models can potentially offer better performance, they require greater computational resources, which is not always feasible in real-time applications. Lesser models disrupt real-time performance, which is crucial for applications such as autonomous driving or real-time surveillance. To address this, a common practice is to deploy lightweight CNN architectures that maintain a reasonable trade-off between accuracy and speed. Complementary techniques like model pruning, where redundant or non-essential network connections are removed, and quantization, which reduces the precision of the network's parameters, can also be utilized to accelerate inference without significantly compromising performance. Data augmentation plays a crucial role in training robust CNN models for video analysis and object tracking. In the context of videos, augmentation techniques can include not only spatial transformations like flipping or cropping, but also temporal ones such as time stretching or frame dropping. This enhances the variety of the training dataset and helps the CNN become invariant to a wider range of conditions that may be encountered during video analysis. By presenting the network with multiple plausible alterations of the input data, a CNN can learn to generalize better, improving its accuracy and robustness in real-world scenarios. Fine-grained classification and object recognition in videos often require the use of attention mechanisms within CNN architectures. Attention mechanisms enable the network to focus on specific regions of the video frames that are more relevant to the task at hand. This is particularly useful in scenarios where the objects of interest occupy only a small portion of the frame or are surrounded by clutter. By prioritizing the processing of these select regions, attention-based CNN models can efficiently allocate computational resources, improving both accuracy and performance in video analysis and object tracking tasks. Despite the progress made in video analysis and object tracking, there remain challenges that CNNs face in these fields. One of the primary issues is the handling of long-range temporal dependencies, since many of the current CNN architectures and their variants are limited to processing short sequences of frames effectively. Solutions that draw inspiration from advancements in natural language processing, such as the use of transformers, are beginning to emerge that might offer new ways to capture these long-term associations. Moreover, the field of unsupervised and semi-supervised learning offers promising approaches for scenarios where annotated video data is scant or labeling is expensive. In practice, CNNs have demonstrated their effectiveness in the field of video analysis and object tracking. They have enabled advancements across various industries and applications, providing the foundational technology for many cutting-edge systems. While there are still obstacles to overcome, the adaptability and continued development of CNN models ensure they remain at the forefront of research and application in computer vision and related areas. As computational power increases and novel techniques in machine learning and computer vision arise, CNNs are poised to make even greater strides in the analysis and interpretation of video data, solidifying their role in the ever-evolving landscape of artificial intelligence. 3.8 Challenges in Training CNNs. Training convolutional neural networks, CNNs, is a complex process that involves numerous challenges. The first notable challenge is the vanishing gradient problem, which occurs during backpropagation, the algorithm used to adjust the weights of the network. As gradients are calculated and propagated backward through the network's layers, the repeated multiplication of small derivatives can lead to extremely small gradients. This means that the earlier layers of the network learn very slowly, as the gradients used to adjust their weights become progressively smaller. In extreme cases, the gradient may vanish entirely, effectively stopping the network from further learning. As a result, although the output layers of the network might adjust their weights effectively, the earlier layers do not, leading to poor performance of the network as a whole. Another problem closely related to vanishing gradients is the exploding gradients problem. This occurs when large error gradients accumulate, resulting in very large updates to the neural network's weights during training. The consequence of this is that the model's learning can become unstable. The network may fail to converge to a solution, or it may diverge by producing NaN values. The chance of an exploding gradient increases with the depth of the network, making it an especially pertinent issue for deep CNNs, which have many layers. Solutions to mitigate these gradient problems include employing normalized initialization of weights and sophisticated optimization techniques like gradient clipping, which can help in ensuring stable learning. The third challenge is overfitting, where a neural network learns the training data too well, including its noise and outliers, but does not generalize well to new, unseen data. CNNs, being highly expressive models with many parameters, can easily overfit if not regularized properly or if trained on datasets that are too small. Techniques to combat overfitting include using data augmentation to artificially increase the size of the training set, implementing dropout layers to randomly deactivate a subset of neurons during training, and using early stopping to halt training when performance on a validation set begins to deteriorate. In addition, regularization methods like L2 regularization can penalize large weights during training, leading to a simpler and more generalizable model. A fourth challenge is the issue of imbalanced datasets. Often in practice, some classes in a dataset are overrepresented, while others are underrepresented. This imbalance can lead the CNN to become biased towards the majority class, resulting in poor predictive performance on minority classes. To address this, practitioners can use techniques such as class weighting, where the loss function is adjusted to penalize errors on the minority class more than errors on the majority class. Alternatively, one can oversample the minority class or undersample the majority class to balance the training dataset, though this may lead to overfitting or underfitting respectively. The fifth challenge involves the computational complexity and resources required to train CNNs. CNNs often consist of a large number of layers and parameters, which demand significant memory and processing power. Training on large datasets can be particularly time-consuming and may require specialized hardware, such as graphics processing units, GPUs, to perform computations in a reasonable amount of time. Parallel processing and distributed computing strategies are sometimes employed to mitigate these computational challenges, but these too can be complex to implement and come with their own limitations and costs. The sixth challenge is the software and tools needed to train CNNs effectively. While there are numerous deep learning frameworks available, such as TensorFlow, PyTorch, and Keras, each has its quirks and learning curve. Selecting the appropriate framework that aligns with the specific needs of the project and becoming proficient with it can be time-consuming and challenging for practitioners. Moreover, the field of deep learning is advancing rapidly, and frameworks are consistently updated with new features and optimizations, requiring continuous learning and adaptation. Hyperparameter tuning presents the seventh challenge in training CNNs. Selecting the optimal set of hyperparameters, including learning rate, batch size, number of layers, number of filters per layer, size of the filters, and choice of activation functions, among others, is critical to the success of a CNN. This process is often tedious and requires extensive experimentation. Although tools and techniques such as grid search, random search, and Bayesian optimization can aid in this process, hyperparameter tuning remains a time-consuming and often frustrating aspect of CNN training. One more challenge with training CNNs is the quality and quantity of the training data. The performance of the CNN is heavily reliant on the data it is trained on, and if that data is of low quality or if there is not enough of it, then the resulting model will likely perform poorly. Cleaning and pre-processing data effectively thus becomes paramount, but this process can be labor-intensive and requires significant domain knowledge. Ensuring that the dataset is diverse and representative of the full scope of data the model will encounter in the real world is also crucial, but can be difficult to achieve. Handling complex patterns and variations in data is the ninth challenge. While CNNs are inherently good at hierarchically capturing spatial hierarchies in data, they can sometimes struggle to recognize patterns with varying scales, rotations, and translations. Although techniques such as spatial transformer networks exist to help CNNs become invariant to such transformations, implementing these solutions often comes with additional complexity and may require more computational resources. Lastly, the interpretability of CNN models can be challenging. Understanding why a CNN makes a certain decision is not straightforward, since the operation of deep neural networks is often considered to be a black box. This lack of transparency can be a major hindrance, particularly in industries that demand a high degree of explainability, such as healthcare and finance. Efforts to improve the interpretability of CNNs, such as the development of visualization techniques like heat maps and tools that can approximate the nonlinear computations of a CNN in more understandable terms, are ongoing areas of research. Successfully overcoming these challenges requires a deep understanding of neural network theory, practical experience in training complex models, a diligent approach to experiment design, and sometimes a bit of creativity. As research advances and the field of deep learning evolves, new solutions continue to emerge, helping to alleviate some of the difficulties faced during the training of convolutional neural networks. The development of new techniques and technologies, along with collaboration and knowledge sharing within the research community, will further contribute to the refinement of CNN training methods and the success of applications leveraging this powerful tool. 3.9 Transfer learning with CNNs. Transfer learning with convolutional neural networks, CNNs, refers to the technique where a model developed for a particular task is reused as the starting point for a model on a second task. It is a popular strategy in deep learning when you do not have an extensive dataset at your disposal. By leveraging knowledge from a related task with an abundance of data, transfer learning allows for significant improvements in the learning process and generalization capabilities for the new task. In the context of CNNs, transfer learning typically involves taking a pre-trained network and either using it directly for a new task or fine-tuning its parameters to better suit the new task. Pre-trained networks are typically models that have been trained on a large benchmark dataset, such as ImageNet, which consists of millions of images across thousands of categories. The intuition behind transfer learning is that features learned by the network on one visual task are often general and can be beneficial for other visual tasks. The first step in transfer learning with CNNs is selecting an appropriate, pre-trained model. The choice of model is contingent upon the similarity of the new task to the task the model was originally trained for. For example, if the original task was object recognition, this model would be useful for other visual recognition tasks. It is important to consider the complexity and depth of the model. More complex models contain a larger number of parameters and are capable of capturing more intricate patterns, but also require more computational resources. Once a suitable pre-trained model is chosen, we must decide which layers to keep and which to retrain or replace. In many cases, the early layers of a CNN, which tend to capture basic visual features such as edges and textures, are retained. Meanwhile, the latter layers, which are more specialized toward the original task, are adapted for the new task. This can be achieved either by retraining these layers or by replacing them with new layers that are trained from scratch. Fine-tuning these layers requires setting an appropriate learning rate, a crucial step in transfer learning. The learning rate must be low enough to make only small adjustments to the weights. This protects the pre-learned features and avoids the catastrophic forgetting of useful representations. Simultaneously, it should be high enough to allow for learning the specifics of the new task within a reasonable time frame. Striking the right balance is essential to the success of transfer learning with CNNs. Data augmentation becomes an important technique when adapting a pre-trained model to a new domain. Because the original dataset might differ significantly from the new task's dataset, augmenting the data with transformations, such as rotation, scaling, and cropping, ensures the model is exposed to a wide variety of data points. This makes the model more robust and improves its ability to generalize from the pre-trained knowledge to the new task. An optional but often beneficial step is semi-supervised or unsupervised feature extraction. Before the fine-tuning stage, one can run the new dataset through the pre-trained model and use the output from an intermediate layer as a new feature representation. This dataset of extracted features can sometimes uncover structures and relationships within the data that were not immediately apparent, and can serve as a robust starting point for the subsequent fine-tuning process. Monitoring the performance of the CNN during the training process is important. When fine-tuning a model, a phenomenon known as overfitting, the model performing well on training data but poorly on unseen test data, can occur. To mitigate this, techniques such as early stopping, regularization, and dropout can be used. Early stopping involves halting the training process once the performance on a validation set ceases to improve, thus avoiding overfitting by not allowing the model to train for too long. Regularization applies penalties to the complexity of the network, discouraging the model from relying on any small set of weights, which in turn promotes the distribution of information across the network. Dropout is a specific form of regularization that randomly deactivates a subset of neurons during training, encouraging the network to develop more robust features that do not depend on a specific set of neurons and thereby improving generalization. The impact of transfer learning in the field of computer vision cannot be overstated. It has enabled practitioners with limited data or computational resources to achieve state-of-the-art results. Many pre-trained models are now readily available and have been applied successfully to tasks ranging from medical image analysis to autonomous driving. Transfer learning has, in essence, democratized deep learning by making powerful models accessible without the need for extensive data or computational power. In summary, transfer learning with CNNs is a powerful tool in the machine learning practitioner's arsenal. By understanding how to effectively leverage pre-trained models and apply them to new tasks, one can rapidly prototype and deploy models with a fraction of the cost and time traditionally involved. This approach not only speeds up the development of accurate models, but also extends the frontier of what is achievable with limited datasets, ultimately advancing innovation in various fields of study and application. Convolutional neural networks, CNNs, represent a significant breakthrough in the field of deep learning, particularly for tasks that involve image recognition and processing. The success of CNNs can be attributed to their specialized architecture, which is expressly designed to handle data with a grid-like topology. Typical applications of CNNs include image and video recognition, recommender systems, image classification, medical image analysis, and natural language processing, among others. However, as the field evolves, so does the complexity of the problems we wish to solve. This drives ongoing research and the development of new techniques and innovations within the domain of CNNs. One of the recent innovations in CNNs is the development of capsule networks. These networks aim to overcome some of the limitations inherent in traditional CNN architectures, such as their inability to take into account important spatial hierarchies between features. Capsule networks use groups of neurons, known as capsules, and dynamic routing algorithms to ensure that the network can learn to recognize objects in a way that takes into account their spatial orientation and relationship to other objects. This is particularly beneficial for tasks that require a deep level of understanding of the scene or object composition, as capsule networks possess a higher level of representational power. Another focus area is the improvement of CNN's efficiency, both in terms of computation and data usage. Neural architecture search, NAS, has emerged as a powerful tool for automating the design of neural network architectures. By leveraging reinforcement learning, evolutionary algorithms, or gradient-based optimization, NAS can identify models that are both highly accurate and efficient. This reduces the reliance on human expertise for designing sophisticated neural networks and enables the discovery of architectures that might be non-intuitive for human designers. 3.10 Innovations and Future Directions in CNNs. The integration of attention mechanisms into CNNs is another exciting direction. Attention mechanisms enable a network to focus on different parts of the input sequentially, mimicking the way humans pay attention to different regions when viewing images or scenes. By integrating attention into CNNs, researchers aim to boost the performance of neural networks on complex tasks where contextual relationships and fine-grained details are important. Attention-based models have already shown promising results in various applications, such as fine-grained image recognition and visual question answering. Adversarial training represents a novel approach to improve the robustness of CNNs. Adversaries are examples that are deliberately designed to deceive the neural network into making a mistake. By incorporating adversarial examples during the training process, CNNs can learn to be more robust against such perturbations. This technique is not just about defending against malicious attacks, it also helps in building networks that generalize better and are less prone to overfitting. As CNNs are increasingly deployed in critical applications, such as autonomous driving and medical diagnosis, ensuring their robustness against adversarial attacks is of paramount importance. The concept of transfer learning has also been a significant boon to CNNs. It involves transferring knowledge obtained from one task to another. In practice, this means that a CNN trained on a large dataset can have its learned features repurposed for a different task with a smaller dataset. This method has been especially helpful for applications where labeled data is scarce. By fine-tuning a pre-trained network, practitioners can train CNNs with much less data without sacrificing performance, thus making deep learning more accessible to problems with limited data resources. To tackle the challenge of ever-increasing dataset sizes and complexity, distributed and parallel training methods for CNNs have gained traction. These methods involve training a single model across multiple machines or processors, thus reducing training time significantly. Innovations in this area include new parallelization techniques, efficient communication strategies to reduce bandwidth bottlenecks, and specialized hardware accelerators. With the rise of big data, these scalable training methods are crucial for keeping the training time of CNNs within reasonable limits, especially when working with high-resolution images or videos. Interpretability and explainability of CNNs have become crucial areas of research. Despite their superior performance in various tasks, CNNs often operate as black boxes, with decisions that are not easily understood by humans. Researchers are actively working on developing techniques to make the decision-making process of CNNs more transparent. This includes methods that visualize the activation of neurons in response to inputs, attribution methods that highlight the parts of input data that are most influential for the decision, and techniques that generate textual explanations for the decisions made by CNNs. Another important trend in the development of CNNs is the use of generative models, most notably generative adversarial networks, GANs. GANs consist of a generator network that creates data samples, and a discriminator network that distinguishes between real and generated samples. This adversarial setup enables the generation of highly realistic synthetic data, which can be used for data augmentation in training CNNs. Moreover, GANs have facilitated advancements in tasks such as image-to-image translation, super-resolution, and 3D object generation, subsequently broadening the scope of what is possible with CNNs. Bio-inspired algorithms have also come to the fore as a source of innovation in CNN design and training. These algorithms draw inspiration from biological processes, such as the genetic mechanisms of evolution or the neuron firing patterns of the human brain, to create more efficient and powerful neural network models. Methods such as neuroevolution, which applies evolutionary algorithms to optimize neural networks, and spiking neural networks, which simulate the way biological neurons communicate, have the potential to transform the landscape of CNN architectures and learning algorithms. In summary, the advancements in convolutional neural networks continue to reshape the landscape of artificial intelligence. With each innovation, these networks become more capable, efficient, and applicable to a wider array of complex tasks. As we uncover more about both the theoretical underpinnings and practical applications of CNNs, we can expect ongoing progress towards more generalized and powerful AI systems. The future directions of CNNs present an intriguing blend of challenges and opportunities that will undoubtedly be the focus of extensive research effort in the years to come. The potential for substantial and transformative gains in performance, accessibility, and understanding within various domains hints at an exciting chapter ahead in the evolution of convolutional neural networks.